Alrighty, thank you so much for joining us for tonight's Connected Conversation, a program conducted by the Idaho Humanities Council. If you're not familiar with our organization, I encourage you to check out our website, idahohumanities.org. I'd like to remind you all that you may submit any questions using the Q&A feature located at the bottom of the screen. With me tonight is Ryan Weeks from the Idaho National Lab. It's an honor to have you with us tonight, and I turn it over to you, Ryan.
Awesome. Thanks, Doug. Thanks for inviting me and giving me an opportunity to share a few minutes with you tonight. I will give you a little precursor. So I'm representing Idaho National Laboratory tonight, but my degree is in communications. When people think of National Laboratory, they think of engineers and scientists. So my degree is in communications. So I'm going to give you a brief overview of a few things. And my role with Idaho National Laboratory is usually giving tours. So what we do with tours is we will bring groups of people out to the laboratory, put you in a bus, and take you out to these facilities. Usually takes 6 or 7 hours. And that is an appropriate amount of time to really tell our story. But tonight, I've got about 30 or so minutes to share that with you. So I'm just going to cram a whole bunch of information into that 30 minutes. And then at the end, we're going to have some time for questions and things like that. So, but when I start talking about nuclear energy and things like that, remember, I'm a communications guy. So, all right, so let's go ahead and get started here. All right, so a presentation tonight, how INL is changing the future of nuclear energy. So how Idaho National Laboratory is changing the future of nuclear energy. And for those of you that aren't familiar with Idaho National Laboratory, I'm sure quite a few of you on this presentation have heard of us. But just to give you a little background, there are 17 national laboratories in the United States. So we're one of those 17. And we're what you call a multi-mission national laboratory. So what that means is that we have more than one focus at our national lab. So if you look right next to us over here in Colorado, there's the National Renewable Energy Laboratory. That's all they do. All they do is renewable energy. But we're a multi-mission. So what that means is we have different directorates and different areas where we do our research and our work. So the one that we're known most for is nuclear energy. And that's what we'll talk about most tonight. But we also do a significant amount of work with national and homeland security, specifically in cybersecurity and wireless technologies there. And then we also, our third directorate is energy and environment science and technology. So when we're talking about energy and environment, we're talking about clean energy sources, batteries, electric vehicles, biomass, microgrids, that kind of work. So even though we're known for our nuclear background, we do a whole lot more than just nuclear. So our mission, our vision, I'll share with you just real quickly. Every organization has one of these, but I love ours. We look at INL's vision. INL will change the world's energy future and secure our critical infrastructure. So securing our critical infrastructure, that's the work that we do with cybersecurity and homeland security. But changing the world's energy future, how do you do that? And our mission is to discover, demonstrate, and secure innovative nuclear energy solutions, clean energy options, and critical infrastructure. So demonstrating and securing innovative nuclear energy solutions, what does that mean? And that is what we'll talk about tonight. And how do we tie that in with other clean energies and also securing the critical infrastructure? So before we go into the future of INL and nuclear energy, I want to talk about the past for just a few minutes. In order to understand our future, it's good to get an idea of the past of INL. And this timeline that you're seeing on this slide, it really gives you actually an 80-year history of not just nuclear energy, but nuclear research in the United States. So you can see in 1942, the very first self-sustaining chain reaction, the very first reactor was the Chicago Pile #1. That's when they first were able to fission an atom and have that sustaining chain reaction. Now in 1942, the focus, and all through World War II, the focus was on weapons and explosives and devices and things like that. Their goal was to end the war. So there was a big focus on weapons production in the early days of nuclear. But after World War II ended, about half of those scientists stuck with the nuclear program, with the weapons program. The other half wanted to look at more peaceful applications for this technology. What else can we do with nuclear? More specifically, they wanted to look at, can we use this to produce electricity? And they had the ideas, they were pretty sure that they could, but what they wanted to do is build and demonstrate some test reactors to find out if the ideas that they had were actually something that were plausible, things that they could do. And a lot of these scientists, they were from bigger cities. Chicago was a big player in the early days. And when they started talking about building a bunch of test reactors, they thought, well, you know what, maybe the suburbs of Chicago are not the best place to do this. And so they formed what was called the Atomic Energy Commission, and it was their job to go out and find some place in the United States that had a whole lot of space, not a lot of people, some place where they could build and demonstrate these reactors. And that's where Idaho comes into the picture. They selected the Arco Desert in 1949 as the National Reactor Testing Station. So that's important to know because Idaho National Laboratory has never been a weapons laboratory. We've always been focused on energy and peaceful applications for this technology. But in 1949, as a National Reactor Testing Station, it really was this idea that if you had some sort of concept, some idea, you could come out and you could build and you could test it out here. So there were a lot of different organizations and groups and laboratories that were testing out here. So the Navy, for one, this is where they built the first prototype for nuclear submarines and aircraft carriers. The Army was looking at mobile reactors that they could maybe put on the back of a truck and, you know, put in remote areas like Alaska to power bases and stations in these remote areas. The Air Force was out here trying to build nuclear powered airplanes. The very first reactor that was built at Idaho National Laboratory, it was built by Argonne National Lab because we weren't called INL back then, but it was the Experimental Breeder Reactor 1. And that happened, they built it in 1949, but in 1951, they produced enough electricity to light a string of 4 light bulbs. That was the first usable amount of electricity ever produced by a nuclear reactor. So this is where we first proved that you could use a reactor to produce electricity. And so they did that. The very next day, they produced enough electricity to light the entire building. And since then, we've actually built 52 reactors. In 71 years, we've been here for 71 years. And in those 71 years, we built and demonstrated 52 reactors. And when we talk about why we built so many reactors, they're all test reactors. We only had a handful of them that ever produced electricity, but all of the safety standards that went into the nuclear industry in the United States, you know, a lot of those came from work that we did at Idaho National Laboratory. So you can see from the pictures, there were some different tests that we did, but we wanted to find out what would actually happen if you had a steam explosion. What would happen if you melted down the core of your reactor? What would happen if your reactor lost its fluid? So in order to understand these things, they did these tests. And you know, that from those tests came all of the safety standards that went into the nuclear industry. What that also did is that created a nuclear energy test bed. So what we have today, we have the capabilities to use these reactors, to use our history to test things. So we have 4 operating reactors now. So of those 52 reactors, we have 4 that are still operating, and they're all test reactors, like the Transient Reactor Test Facility. We call that the TREAT reactor. That is a transient test reactor. What that means is if you want to design a new fuel, say it's an accident tolerant fuel, you want to design a new fuel that can withstand an accident, you have to be able to test that accident somehow. So what we do is we put it in there, the fuel in the TREAT reactor, we hit it with a huge amount of energy, and we try to destroy that fuel. So whether we're going to melt it, you know, vaporize it, basically destroy it, But if it survives, then we know we've got an accident-tolerant fuel. So you have to be able to create that accident environment. The Advanced Test Reactor, largest test reactor in the world. That one is really learning how to age materials in a short amount of time. So if you want to figure out what 50 years of irradiation is going to do to a certain material, you can put it in the Advanced Test Reactor. In just a couple of years, you can have 50 years worth of neutrons damaging that material. So to give you a comparison, for those of you without a nuclear background, what that might mean, say if you're in the auto industry and you have a new car, if you want to see what happens to that car when you slam it into a concrete wall, that would be like the treat reactor. That's an accident scenario. If you want to figure out what that car is going to do after driving at 300,000 miles, that would be like putting something in the Advanced Test Reactor, going through that aging process. But what we don't have at INL is a fast reactor. A fast reactor is a test reactor that's going to be used for a lot of advanced reactor designs that we'll get into a little bit later. But we had that capability up until 1993 with the Experimental Breeder Reactor 2. When that was shut down, we lost that capability in the United States. There's actually a plan to rebuild what's called a versatile test reactor, which will be a fast reactor, which will be another way to test advanced reactor designs and fuels. We don't know for sure that that's going to be built at Idaho. We kind of think that that's the direction that we're headed, but it's not official yet. So that will be just another opportunity for us to have this nuclear test bed to do all of those different tests. So with the history, so in 1949, it was the National Reactor Testing Station. It's gone through a couple different name changes over the years. Sorry about that. But in 2005, what we did is we took that almost 50 years of experience and we put that all under the same umbrella with all these different laboratories and contractors. And we created the Idaho National Laboratory. And at that point, we decided, what is the future of Idaho National Laboratory going to be? And it's going to be advancing nuclear energy, securing and modernizing critical infrastructure, and enabling clean energy systems. So that leads us to the title of the presentation today, the future of nuclear energy. So recently, Congress designated Idaho National Laboratory as the National Reactor Innovation Center. So what does that mean? Well, for me, in my head, this is like National Reactor Testing Station Part 2, where if you have an idea or concept, you can come here and you can get the help that you need to prove that. So there's three technology levels. There's the first one, proof of concept. We got all these ideas, industry, universities, they can come in with ideas. We got to decide, okay, is that an idea, a good one? Is that actually feasible? Is that something that'll work? Once you pass through that, then the next level would be the proof of performance. Let's do some modeling, some simulation. Let's start doing some tests. Let's irradiate some materials. Let's validate some data. So is this actually a thing that could possibly work? And then the last level would be actually building it and demonstrating that reactor. So you can do all of the research that you want in the laboratories and on computers and modeling and simulation, but until you actually build the reactor and you operate it, we don't know if it's going to actually work the way that we planned. So that is really our bread and butter there, is building and demonstrating. That's what we've been doing over our 70-year history. And so one of the ways that we are bringing these innovations into to INL is through a program called GAIN, Gateway for Accelerated Innovation in Nuclear. And what this is really, if you have an idea like an industry, university, utilities, other partnerships, this is really giving them access to the national laboratory system. So they can bring those ideas and we can flush them out, we can test them out and see, maybe if they need some extra funding, things like that, that we can actually move forward on some of these ideas and on advanced reactors, fuels and designs. So let's talk about advanced reactors. What does that even mean? So the future of nuclear reactors, what do they look like? Here's a picture of a control room. When we build these new reactors, are they going to have the old dials and toggle switches and things that they had, that current reactors have that were built in the 50s, 60s, 70s, and 80s? They're not. So, how are we going to do that? This is a version of a digital control room. So let's look at a digital control room. How does that going to work with a reactor? What are the cybersecurity concerns with a digital control room? How reliable is that? So we've got to flush all those things out. And so we have, a team that's dedicated just to that. Looking at advanced fuels. So this little fuel down here at the bottom of the screen, that's called triso fuel. And that thing is only about as big as the lead on your pencil. A little teeny tiny piece of fuel. So the little teeny tiny piece of uranium about the size of a poppy seed that's surrounded by a couple layers of cladding. So that makes it, that's just a safer fuel design. A lot of commercial reactors, they have these big fuel rods where if the cladding gets damaged, then you're exposing all of that fuel. So having a little teeny tiny little poppy seed fuel, or if that gets damaged, that's, less of a concern. Another one, this is a really cool story. It looks like just a pile of yellow laundry detergent, but that is HALEU. HALEU stands for high assay low enriched uranium. And it's a cool story because what we're doing is this dome down here, that was the experimental breeder reactor 2. It operated for 30 years. It produced about a third of the electricity for the site for those years when it was operating. But the fuel that was used at EBR2 has just been sitting basically in storage, waiting for a place, a national repository where it would be stored. So basically, it was spent fuel. It was considered waste. But what we've done is we've taken that fuel and we have blended it down into this high assay low enriched uranium, and that is now a feedstock for these advanced reactors, a feedstock that they can use for fuel designs and for fuel fabrication and things like that. To really test out these new fuel ideas. So what we've done is we've taken what was waste and we've turned it into a fuel source that reactors can actually operate off of. And then another thing right here, this EBR2 dome, it still exists. The reactor was shut down in 1993. It's gone, long gone. It's just an empty dome. But we have that dome and other facilities where we can actually build what are called microreactors, small reactors, put them in there, put them in the secure area, test them out and demonstrate them in places like this dome and a couple other facilities. So I mentioned microreactors and advanced reactors a little bit. So let's talk about those because they're really cool. First, let's talk about small modular reactors. So for years, every nuclear power plant in the United States was built one at a time, where somebody had a plan, they got that plan approved, and then they built it. And so each one of them are unique and different and individualized. The problem with that is they're also very expensive. The last 2 nuclear power plants in the United States have started building and then they've been stalled because of financial problems. So how do you cut down, the financial problems of building new reactors? So with small modular reactors, the way that they're designed is pretty cool. Is it's actually not just one big reactor, but it's a set of 12 little reactors. And so you can have the entire 12 pack, or you can just have 1 or 2, depending on how much energy you need to produce. So one of these reactors can produce about 60 megawatts of power. So in the energy world, we say a 1 megawatt is about 800 houses. So if you've got 60 megawatts, I am from Idaho Falls, so I could power all of the houses in Idaho Falls with one of these little reactors. So maybe if you're a city that only needs 2 or 3 of these, that's all you build. But if you need all 12 of them, you can get up to the point where you're producing 720 megawatts of power. But the other idea is that they're all tested, they're all licensed the same, so that you could build these in a factory, you could put them on a truck, you could truck them to the site, and you could assemble them on site, and they're all the same, they're all work the same, they're already approved, and that's really going to cut down the cost of building a new nuclear reactor, a new power plant. Another one is microreactors. Microreactors are really cool. These are anywhere from 2 to 20 megawatts, so little itty bitty reactors, but there's a couple different applications. As you can see, all the logos on this slide, there's a lot of companies, a lot of organizations that are interested in demonstrating microreactors. There's some defense applications. You can see this one here in the truck. The Department of Defense is looking into microreactors because they have their bases and their stations off in these countries, and sometimes they have to move and go different places. But one of the most dangerous parts about that is with these bases is that they are trucking in diesel, and diesel convoys are a big target. You know, if you take out a diesel convoy, then that's awesome. So it's extremely dangerous to be trucking diesel in. So the thought is, if we could have this small modular reactor, or sorry, not small modular, this micro reactor that you put on the back of a truck that can provide you with all of your power and your energy needs, and you're not trucking in all that diesel. And then when you need to leave, you can just put it back on the truck and you can move it. So that is a big interest with the Department of Defense. But you look at the commercial applications of that over here. This first picture is an example of that. That is Oklo. Oklo is a company that is looking at microreactors. And the thought here is, how can you use these commercially? So the best example I have is, you think about Alaska. There are fishing villages, there's little communities, there's all over, you know, those little villages and communities that need power. And what are they doing right now? They're flying in diesel and they're running off generators. So not only is that terrible for the environment, but it's also very expensive. So if you can, you know, station one of these microreactors in those villages, and you can provide power for that without having to fly in all that diesel, that is just adding another, you know, carbon-free source of electricity that's reliable for those villages. And the cool design here, Oklo is one that actually would be using the HALEU fuel that I mentioned earlier, coming from EBR2. But their design, the very top of this A-frame, is actually a community center. So we've looked at safety standards, everything that needs to go into securing these microreactors, and they figured that they could build a community center right on top of the reactor. That's how safe it would be. So it's a really cool concept. Both of these are, there are plans already in place, as well as the small modular reactors, to build those at INL. So microreactors and small modular reactors are really talking about energy production. So what can we do with reactors beyond just producing electricity? So there's a concept here that we have is called hybrid energy systems. So hybrid energy systems are an energy system that we work with the grid, and we try and figure out, how do we get, you know, renewables like wind and solar to play well with base loads like nuclear? Because when the wind starts blowing and the sun starts shining and you're getting all that electricity, it doesn't make a whole lot of sense just to turn off your reactor and then hurry and turn it back on when the wind stops blowing. That's not great for the reactor. It's not great for the materials and the fuels and things like that. So what can you do? How do you make those two play well together? So the thought with this hybrid energy system is, when the wind starts blowing, the sun starts shining, you get that electricity that's being put on the grid, is you can divert the heat and the energy, the heat and the electricity from that nuclear reactor to do different things. So maybe it is creating hydrogen. Maybe it's doing water desalination, so you're cleaning water. Maybe you're using that heat for new chemical processes, or you know, chemical companies use a lot of heat with their processes. Maybe you're making ammonia. There's a lot of different uses for that. But getting those base loads and those, you know, intermittent, those renewable sources that are going back and forth to kind of play well together. And what does that look like? This is a picture of the laboratory where we're working on that. And what we've got here is, we've got a real-time digital simulator where we're hooked up with the National Renewable Energy Laboratory in Colorado, and we're receiving their real-time wind and solar data. And then we've got a thermal loop, which simulates the heat from a nuclear reactor. And then we're producing hydrogen over here. So how do we get that to work? And the reason why we focus on hydrogen is, a lot of industries use hydrogen. So it's used in fertilizers, it's used in plastics, it's used in like steel production, a lot of different uses for hydrogen. And right now, 95% of hydrogen is produced using natural gas. So if you were looking for a clean source of hydrogen, then doing that would be great. But also what that does is that gives us another revenue stream for our current fleet of nuclear reactors. Some of those nuclear reactors are struggling financially. One that we're working with is the Davis-Besse power plant, where it's either in bankruptcy or close to bankruptcy. But if you can add another purpose for that, another revenue stream, while it's creating hydrogen, then you can keep that online and you can keep it producing electricity as well. Because the more reactors that we shut down, we have to figure out how to replace those. And if we're not going to replace them with wind and solar, we're going to replace them with something that's, has carbon emissions. And so if we're serious about reducing the carbon emissions and the carbon impact in this country, then nuclear has to be part of the conversation. And there's other parts of this lab too. As I mentioned before, we do a lot of battery testing, wireless charging for electric vehicles, a lot of work that we can do. How do you get wireless chargers? If they're online and they're creating spikes in the grid, how do you even that out? So there's a lot of different work that we do with this hybrid energy system that if we had a little bit more time, we could go into detail with. But it's some pretty exciting stuff. Other applications beyond just power production and beyond, I guess, this planet, as we have our space applications. We assemble what are called RTGs, radioisotope thermal electric generators. And right here in this picture, that white contraption that they're holding, that's a radioisotope thermal electric generator. And what that does is that can power those deep space missions for NASA. For example, New Horizons that flew by Pluto a couple of years ago was powered by an RTG that we assembled here at Idaho National Laboratory. Also, this is a picture of Curiosity, the Mars rover that is on Mars right now. And you can see back here, there's the RTG. We assembled that one. We also assembled one for Perseverance. Perseverance is the next Mars rover, and it's actually down ready to be launched. Its launch window officially opens on the 30th of July, so just in the next 2 days, and it goes through about the middle of August. So that could be launching anytime within the next month. It could be launching in a couple days, so that's pretty cool. Other applications is we're looking at nuclear propulsion. So once you get into space, can you use nuclear to propel things back and forth and to go different places? A new project that we just announced a couple days ago would be surface fission power systems. So what that means is, can we put a reactor on the moon and use it to produce electricity if we're going to build a space station or something like that up there? And then the next step would be Mars. Can we have power generation at Mars? So we're already thinking about the next step and how are we going to get electricity and power up on those different planets. So that's pretty cool. And then, of course, I want to throw in partnering with Idaho. A big part of what we do is because of our relationship and our partnerships with Idaho. These are 3 buildings in our Idaho Falls campus: the Center for Advanced Energy Studies, the CyberCore facility, and the Collaborative Computing Center. These are all Idaho-owned buildings, and they're all partnerships with the University of Idaho, Boise State, and Idaho State University. So Center for Advanced Energy Studies is looking at materials testing, renewable sources, geothermal, all kinds of things there. The Collaborative Computing Center and CyberCore were recently built. They just came online in October. But I talked about Homeland Security and CyberCore. If these guys and ladies, if these researchers were anywhere else in the world, you'd call them hackers. But since they work for INL, they're cyber researchers. But they're really looking at securing critical infrastructure, transportation, pipelines, utilities, power plants, including nuclear power plants, and really, doing that work there. It's some very, very important work. And then the Collaborative Computing Center, we do a lot with our supercomputers there, but one of the things when it comes to nuclear that you're going to do is when you are designing new nuclear reactors, there's a lot of modeling and simulation that's going to go into that before you ever even do a physical test. So we recently installed, just a couple months ago, a supercomputer. It's called Sawtooth. When it was installed, it was the 37th fastest supercomputer in the world. So a lot of work there, and the universities can use those supercomputers. So what we're doing is we're building a pipeline. We're working with universities and professors, one for the nuclear industry, but also for cybersecurity, for engineering, for supercomputing, just building that pipeline to feed into the future of energy and what that looks like. So what is the future of nuclear at Idaho National Laboratory? I think it's bright. I think it's exciting. You can see here those 52 reactors that we've built. How many reactors we've had operating by year. Back in the 60s and 70s, it was really exciting. We had a bunch of reactors operating. Then during the early 90s through the 2000s, we just had the 3 that we maintained and we operated. In 2017, we brought the treat reactor, the one that does the accident testing, online. And really the future is exciting with the microreactors, the small modular reactors, the other things that we're doing. The future is really exciting, and we're hoping to build and demonstrate and get back to what we do best, and building and demonstrating reactors, and hopefully, changing the energy future and improving, life on this planet. So anyway, that is the future. If you have any questions, I guess right now would be the time that we open up for that. I'll turn it back to Doug for that.
Yeah, thank you for a very informative presentation. I did not know anything that you're talking about, so definitely learned a lot. Now we have two questions. The first one is, are you, as the INL, involved in recycling batteries at all?
We do a little bit, but what our focus on when we talk about recycling, what we're looking at is rare earth metals. So right now we're getting the majority of our rare earth metals from China, the United States is. And so rare earth metals go in all kinds of things like windmills, they can go into jet pilots, all kinds of stuff. So we're looking at different recycling technologies, not just for batteries, but for rare earth metals. Now, if we could, like electric vehicle batteries, if we could use them for grid storage, we're looking at that. Maybe instead of recycling them, we just pile them into a shed next to a wind farm and use them for grid storage. So yeah, there's some different applications there. It's not one of our major focuses, but we're definitely involved in that a little bit.
Nice. And then what is the situation with spent fuels?
Spent fuels. So that's fun to talk about. Everybody wants to know that. So it's a political decision. We have proven since the early 60s and 70s that we can recycle fuel, but it turns out that that's not the most economical thing to do. And so a lot of we don't do it in the United States. France recycles fuel. So it's really a decision of the nation. Are we going to build a national repository somewhere? Right now, commercial fuel is being stored on site with the reactors, and it's fine there. It's been there for years. It could be there for more years. But until the nation decides if we're going to go the direction of recycling, or if we're going to go the direction of actually having a national repository to store it. So we don't get involved in the policy. We just provide the science. It says, yes, if you're going to recycle, you could do it this way. If you're going to store it, you should probably look into these things. So that's really a political question of whether the nation's, what direction the nation's going to decide to go there.
And then what is the life expectancy of a reactor?
That's a good question. I mean, the current fleet right now, some of them have operated 60 years and are working on extending to another 80 years. These microreactors, some of those microreactors and small modular reactors are looking at only having to refuel every 5 years. So it's really, there isn't really a life expectancy per se, as long as you continue to upgrade and do the maintenance of, the pumps, the valves, the systems, things like that. I mean, some reactors have shut down, but some reactors we've only limited because it's a new technology, I guess, is that we've never operated anything over 100 years, so we don't know. But we can stop and, some of them were licensed for 40 years, and then they looked at that and said, okay, we can go another 20 years, and now they're looking at going another 20 years. Maybe in 20 years, they'll look for another 20 years. So it all just kind of depends on the design and how much effort you want to keep putting into maintaining them.
Yeah, and you brought up a really good point that nuclear energy is still such a new concept. It's not something that's been around forever. It's definitely one of the modern energies. Right. And earlier you mentioned one of the reactors filing for bankruptcy or already in that process. So in that scenario, what would happen if a reactor actually did have to file for bankruptcy? Would they just shut down until someone bought them or they were repurposed?
Yeah, once you shut down a reactor, you're pretty much not going to bring it back up. It's pretty much done. So that is a big part of our mission, is maintaining the current fleet. Because as I mentioned earlier, if you take that reactor offline, then you've got to replace it with something. And if you can replace it with something wind and solar, carbon free, awesome. But I don't know that we're always there yet. So we do a lot of work in maintaining, okay, how do we keep these up and going? How do we get them so that they're producing? And really, you know, there's a lot of that goes into that, like carbon credits and things like that, and that are kind of hurting the cost of nuclear energy that I probably shouldn't get into right now. But but the goal for us is to keep as many of them running for as long as possible.
Now, what is the Idaho National Lab doing to help like the new graduates and the young people in Idaho to get ready for jobs offered at INL? Because it seems like there is a large breadth of positions that you can work within the Idaho National Lab outside of just being like an engineer.
Yeah. So one thing that's super important is we're helping develop, you know, courses. So we have, all of the universities have offices and lab space. The Idaho universities, so Idaho State, Boise State, and University of Idaho have offices and lab space in our facilities. But we're also working with professors to develop the curriculum that we need to, you know, have them qualified to get jobs at INL. So for example, there's schools that are doing really good at cybersecurity and schools that do really good at engineering. But if you have a cyber engineering focus where maybe you're actually building a control system with cyber in mind, you know, crossing between the cyber engineering, you know, that is something that we're working to develop a workforce of people that we actually need and that the nation needs to actually build these hybrid energy systems to secure the grid and things like that. So we're definitely working with curriculum. We have about 350 interns every summer that the universities can come and apply to. We have multiple positions where the professors come and spend time at the lab, or the laboratory engineers and people go out and they teach classes at universities. So we work real close, at least with the Idaho universities, on doing some of that stuff.
Nice. Then, do you know what the mix is of nuclear research done by or done at the Idaho National Lab between companies, the Idaho National Lab itself, and the universities, since they have all the office space there?
So it's really a collaboration.
Okay.
So look at the Center for Advanced Energy Studies. It's the Idaho universities, the University of Wyoming, and then INL. Any project that goes into there has to have at least 3 of those partners on it. So if the 3 universities are working together, you know, they're doing it on their own, but mostly it's INL and a couple other universities. So it's not a whole lot of independent stuff, but mostly we're all working together, collaborating on different things. I can give you a real quick example of that. We've got a microscopy and characterization suite. We call it the MAX suite, where we've got about $9 million worth of microscopes in there. So Idaho State is really good at nuclear engineering. Boise State is really good at materials science. INL brings $9 million worth of microscopes, and we can collaborate the 3 of those together and start looking at some nuclear materials research on, you know, a microscopic level.
Nice.
I don't know if that really answers your question, but.
Oh, no, it definitely did. Now going to the infrastructure of a reactor itself, does the reactor produce electricity directly, or does it end up producing electricity as like a byproduct of like steam turning turbines and stuff like that?
Yeah, it's steam. So you look at power plants, you know, like whether you're burning coal, whether you're burning natural gas, you're trying to get heat to turn into steam to turn a turbine power generator, right? So with a nuclear reactor, what you're doing is you're splitting an atom. When you split that atom, it releases a bunch of heat and energy. So you basically just capture that heat, turn it into steam, turn a turbine, you know, power a generator. So it's basically, you know, the same concept of a power plant. We're just getting there in a different way.
Nice. And then the city of Boise has the goal to have clean electricity by 2035. Is the city working with you guys and your nuclear reactors to reach that goal in any way?
The city of Boise? I'm not sure about Boise. So what we're working with the small modular reactors is UAMPs. So UAMPS is the Utah Associated Municipal Power Suppliers, and that includes like Idaho Falls Power and several other municipalities in Utah. I don't know about Boise, but the goal with that is they're going to use, of that 12 pack, is they're going to use that 10 of those reactors to produce electricity as part of their carbon-free plan. And then the other 2 reactors are going to be for INL to do experiments with hybrid energy systems, let our cyber guys throw rocks at them and see what happens. Just basically do some research on what a small modular reactor does, and so we can play around with it, since this is the first time that it's ever been built. So I should have known a little bit more about Boise, but I don't.
And with the piloting the safety processes, I'm just curious, has there actually been anything like bad that's happened while Idaho National Lab was doing these pilot tests with the nuclear reactors?
Well, so
And
one of the most interesting tests was the loss of fluid test. The loss of fluid test is basically what happened at 3 Mile Island. So when 3 Mile Island happened, those guys were actually on the phone with the Idaho guys and saying, okay, what's going on here? So that was a real life application to what was going on. As far as bad things happening in 1961, the Army was operating a reactor called SL1. There was a steam explosion there, which was not intentional, and it ended up killing 3 operators. So that wasn't necessarily a test. It was just, there's a lot of interesting things that go into there, but we learned a lot about reactor designs from that accident and said, okay, let's not build them like this anymore. But as far as like the ones that we actually had steam explosions and meltdowns intentionally, we did that in a controlled environment so that it really didn't, it didn't hurt, or, you know, we did it very carefully, because that's what a national lab can do.
Yep.
Yep. So we did have one accident out here, the SL1, which is a fascinating story. If we had more time, I'd go into it, but that happened.
Now, since reactors, or at least the traditional reactors, are very large, how do you go about modernizing the very old ones that are still active and just essentially bringing them up to date from like the old control rooms with the knobs and the dials to a modern one, if that is possible?
It is, and that's one of the concerns. The graphic that I showed you of the digital control room, that was actually a analog control room that had been digitalized.
Oh, okay.
So what we've done is we've brought in like operators to work on that, and say it's part of a human factors lab. So say you got the nuclear reactor is going to shut down for a couple of months to do maintenance or whatever. Let's bring in the operators and say, if we put this knob, if we replace it with this screen right here, how is that going to work with your reactor? Is that going to work? So we can do that all on a digital screen, and we can move things around. That way, when they get to their shutdown, you know, where they actually have to cut through metal and rewire and do things like that, they can just do it right off, because we've already done all of the research and the human factor stuff for them. So we try to support them as much as they can there. That is a little bit tricky because, I mean, some of those nuclear reactors, you know, some of them are buying parts on eBay because they don't make dials like that anymore. So, you know, it's a thing that we have to address, is as these get older, we've got to update some of that older control room stuff. So we try to help them out with that.
And from my understanding, it seems like the Idaho National Lab has probably like 3 main missions that you guys focus on. Is it challenging to, oh, you're good. Is it challenging to balance all 3 of those? Or does it actually like real world like carry out pretty smoothly to balance the 3 different missions that you guys have?
Yeah, I think from being in the communications office, I don't really know the intricacies of funding and programs and things like that, because you do have to consider all of the other national laboratories and what they're working on, and you don't want to do the same thing that the National Renewable Lab is doing. You know, you don't want to, you're using tax money, so you don't want to be duplicating the efforts. But I think our focus is we want them to tie in with each other. So, you know, when we're looking at renewable energy, we want to figure out how does that tie into a hybrid energy system, or how does, you know, securing critical infrastructure help with our own, control systems, things like that. So I think that we intentionally get them to, fit together like that.
And we do have another question from one of our attendees. Some of us have the impression that nuclear reactors are like the ones depicted in the China syndrome. How many reactors are operating in the US today, and how many of them are like the California China syndrome reactor, and how many are built with newer technology or updated to newer technology?
So this is unfortunate because I don't know what the China syndrome is. But let's see. So I believe there's 98, a couple of reactors have shut down recently. So there's either 96 or 98 reactors operating in the United States. And they are all light water reactors. So they are this technology that was created in the 50s and 60s, and that's when we built them. So as far as advanced, small modular, micro, those kind of reactors, that's the goal, is we want to start building those instead. That's the future of nuclear energy, is getting smaller. So of the ones that are operating today, they are, those ones that were built years ago.
And I did a quick Google search on China syndrome because I also was not 100% sure. And it's the style of reactor where it's the giant concrete tube kind of going up into the air, like curving inwards a little bit. That style of reactor.
Okay. Yes. Yeah. So that is the current fleet. The 96 or so that are operating right now are of that style that were, designed in the 50s, 60s, 70s. So I mentioned there were two projects that they wanted to build reactors like that, but they have been stalled in the United States because of financial issues, and we don't know if they're going to get done or not. So that's when we said, okay, if the last two that we tried to build aren't going to work, then we obviously need to do something else. So what's the new solution? What's the advanced reactor? What does fuel look like? All of that stuff. What do we need to do different to keep this energy source online?
Now, earlier in your presentation, you showed, when you're talking about the microreactors, I believe, there was almost kind of looked like a park, that reactor, where it had like the white roof. Is that, or would something like that be able to output similar amounts of electricity to the older style, where it's the giant concrete China syndrome style? Or would you need multiple of that style to get the same amount as like the older?
Yeah, so with a microreactor, you're looking at maybe 2 to 20 megawatts. So very, very small. So if you do the math, that's like 1,600 houses maybe. So that's not, unless you're going to put multiple ones in a certain city, that's not really what the purpose is there. Now, a small modular reactor, if you do all 12 of them, you can get up to 720 megawatts, and then you're getting closer to what one of those big ones would be. But no, you would have to do multiple of the small ones to equal the bigger ones.
Okay. And another just random question on my end, at least, with the older reactors, is there a way that either you guys have or other national labs to make them like look less of an eyesore? Because I know some people would view that as an eyesore. So I was just wondering if there's any like research you guys have done as a way to like combat that, or that imagery and impression of the older reactors.
I don't know if anybody's looking into that. I don't know if we can just, universally give them a new paint job or something. But
Yeah,
I think what we need to work on there is education. The nuclear industry in general has done a terrible job of educating, because you see these towers and all of this stuff coming out of them, but what we don't say is that's steam. That's water vapor. I mean, it's not like we're polluting. It's not carbon. It might look eyesore, but if you have the education to understand what's actually happening in a nuclear reactor, then they're actually pretty cool. So I think that would be our best way to combat it, would be education versus repainting everything. I don't know.
Yeah, that was coming more out of my urban studies classes from college. Like, just curious, like, how would that affect it? And I think just the impression from history of nuclear reactors, since it is still so new, when something bad happens with one, I feel like it is all over the media, whereas no one highlights the benefits of it. So like we all know Chernobyl, so we all kind of
Right.
have that like, ooh, that's bad. I don't want to live near it.
Yeah.
And are any other countries installing the smaller modular reactors that the US is dabbling with?
Um, Other countries have other ideas. So I don't know that they're specifically like ours, but yeah, other countries are looking at that. So China is actually, building a bunch of the big reactors. Russia is always there, doing new ideas, doing things like that. And that is really, there was, and this gets into the education part again, is there was those years on that graph that I showed you where you're just maintaining reactors. This is a American technology. This is where it was invented. This is where it first happened. And we were the leaders for so many years. But then in the 90s, when we kind of just started saying, yeah, we're done with nuclear, we're not interested in that, those other countries kept going. And so America has kind of lost its footing as a leader. And so we want to get back into that because we're thinking, when there's other countries that are looking for leadership in this, do we want them going to the Russias and the Chinas and the other countries to like that to get their nuclear knowledge? Or do we want them coming to America where things, where we've looked at the safety aspects, we understand why it's important, and we've regulated it very strongly versus what those other countries may or may not be doing.
Then Idaho Power's run numbers to show that even with the highest possible carbon tax, nuclear is possibly not as cost effective, and it won't be included in the Idaho Power portfolio. In your opinion, and given your knowledge working for the Idaho National Lab, in the future, how realistic is nuclear energy as a long-term wide-scale power source?
I think it's very realistic. I think it has to absolutely be part of the conversation. I don't think, there's a difference between base loads and, like wind and solar, they're not base loads. So if we're going to cut out coal and natural gas and carbon emissions, what are we going to replace it with? So of course, small modular reactors right now, they look expensive. This is a brand new technology. And until we actually build it, understand it, and then, like to the point of small modular reactors where they're, basically being built in a factory, we're not going to completely understand what the costs are associated with them. But, we've got to do that research. We've got to build the first one and we've got to understand it. So maybe the first one doesn't make financial sense at all, but 20 years down the road, we're like, hey, yeah, this is good. We figured out, we've worked out the kinks, we've got the bumps out. So yeah, this makes sense now. But we don't really know that until we do the research.
And then with those small reactors, are they expensive just to produce, or are they also expensive to maintain, or is it a combination of both?
I hate to admit, but I am not an expert on the financials. But the goal with small and micro reactors is to cut down cost and make it, easier to build and maintain than the big ones that they have. And maybe there's some different policies that need to be put in place with renewables and carbon credits and whatever. I'm not an expert on that, but that's the goal. The goal is to make them cheaper and better and safer and more efficient and less waste, all that stuff. That's the goal.
And with the smaller units, what do they do with the heat that they produce from functioning?
So if it's just a regular reactor, they're going to put it on the grid and they're going to use it for electricity. If it's part of a hybrid energy system, when they're not producing electricity, they're going to be doing other things, creating hydrogen, cleaning water, all the other things that I mentioned. So yeah, it's just going to be another component, put it on the grid. Like with the UAMPS one, like I said, the 10 reactors that are producing electricity, they're just going to, give that to their ratepayers and everything like that.
Yep. And then earlier you mentioned with all the national labs across the US, how some of them still dabble in the weapons aspect. Are there any that are solely weapons focused?
I believe, yes. I can't speak intelligently to that, but I think Los Alamos's might be, but I don't really know for sure which ones are just weapons, but we do have weapons labs in the US.
And then how familiar are you with the proposed reactor that Bill Gates, I guess, is talking about, and if the INL has participated in the development of that?
Yeah, absolutely. So it's his company is called TerraPower, and Bill Gates has actually come out to INL and toured our facilities. Unfortunately, he came about 6 months before I got the job, so I missed out on Bill Gates. But yeah, one of the technologies that we're using, that we're looking at with TerraPower, is a different way to fabricate their fuel. So it's different from the traditional way and never been done before. So we have a facility dedicated just to TerraPower to fabricate the fuel in that certain way. And then we do all the examinations and the research and the tests like that. So that is another thing, is that reactor is one that would benefit from having a fast reactor like the versatile test reactor. Because right now there are very few fast reactors. Like if we wanted to do a test on a fast reactor, we would have to take it internationally. And right now there isn't a whole lot of nuclear tests that are lining up to go and be put in a Russian reactor. That's probably something that's not going to happen right now. So his company would definitely benefit from the virtual test reactor, but we're doing other things, versatile test reactor, but we are definitely working with them and doing what we can with what we have now.
And then this is more of a policy question. With the waste produced by the small modular reactors, does the waste have to remain in Idaho in perpetuity? And then also, just because I'm curious, what do you guys at the INL do with the waste? Do you study it? Do you try and repurpose it?
Okay, so yes. So the small modular reactors right now I would assume, I don't know that all the details have been fleshed out, but under its commercial license, they would probably be just like any other commercial reactor where the waste is stored on site, unless unless we designate a national repository, which at some point was going to be Yucca Mountain, but that was shut down. So, and what do we do with the waste? So yes, we can look at the waste that we have. The majority of it is just stored on site, but like I mentioned, the EBR2 waste, we pulled that out and said, hey, we can still use this as fuel. So for years what we did is we took all of that spent nuclear fuel and we recycled it and we put it into new fuel. And that's what we did for years and years. And then until I think in the 80s, we stopped reprocessing as a country. So from that point, we basically just stored it and put it there. So yes, so it is hanging out in Idaho. Now, there's another part that people like to talk about, and that is the Idaho Cleanup Project. So for years, we accepted the waste from weapons reactors, or not weapons reactors, but from weapons laboratories. They were under the Cold War pressures that said, hey, we got to build these weapons. We got to go. What do we do with the waste? Just put it in a barrel in a box, ship it to Idaho, and we'll deal with it later. So there's a organization separate from Idaho National Laboratory called the Idaho Cleanup Project. And that's basically what they're doing, is they are taking that weapons era waste, they are digging it up out of the ground, repackaging it, and shipping it out of the state. So that work is definitely happening out on the same desert as we're doing that. It's just a different organization that does it. So the weapons waste is getting rid of, but as far as spent nuclear fuel, there isn't really a place to put that yet.
And if the US starts to repurpose the fuel again in the future, is the current reservoir of spent fuel that you guys have right now, is that still viable to be repurposed into fuel?
Yep.
Even though it's just sitting there?
It's like a gold mine sitting in a landfill. All we need is